This lesson is on solving systems by elimination. In this section, there are some steps involved to help us solve system of equations by elimination. Our first step is to write the system so that like terms are aligned, meaning your x's are lined up and your y's are lined up. The values that stand alone are all lined up, given two equations. Our second step is we're going to eliminate one of the variables and solve for the other. Our third step, we're going to substitute the value of the variable into one of the original equations and solve for the other. And then we'll write our final answer for step 4 as an ordered pair, x comma y, and check our work. So let's go through some examples here for this section. Our first example here, it says solve y plus 3x minus 2, and we have another equation, 2y minus 3x equals 14 by process of elimination. So we have to think back to our 4 steps from the previous slide to help us solve this. We first have to check both of the equations to make sure that the like terms are aligned, meaning they line up. Notice my y's line up, my x's are lined up, and my numbers that stand alone are lined up. So once my variables are aligned and lined up, we can look at and eliminate one of the variables. Well, look at this. When you're working with elimination, you kind of think of adding the y's together, adding the x's together, and the numbers that stand alone. If I look at my x's here, a positive 3x plus a negative 3x, that becomes 0. When I add my y's, 1y plus 2y is going to give me 3y minus 0 equals, now we're going to add up our numbers that stand alone, negative 2 and 14, which becomes 12. So when I write this out in the simplified version, I have 3y equals 12. Now I can solve for y by dividing 3 to each side. So my y is going to equal 4. Now that I've solved for my y, I go and look into step 3 where I'm going to substitute the value I solved for back into one of the original equations to find the other variable. So since I solved for y, I'm going to take y, my 4, choose one of the original equations to plug 4 back into y, so now I can solve for my x. So I'm just going to choose the first one. It doesn't matter which equation you choose. Y plus 3x equals negative 2. Here again, I substitute 4 in for y, so 4 plus 3x equals negative 2. I'm going to subtract 4 to each side. Oops. So I get 3x equals negative 6. Divide 3 to each side. So now I'm going to get x equals negative 2. So I've now solved for my x and my y. I can now write this as an ordered pair of negative 2 comma 4. And that is my final answer. But I do need to check to make sure this ordered pair that I solve for, it makes both of these equations true. So if I set it up here with my equations, my y4 plus my 3 times my x, negative 2. Does that equal negative 2? Well, 4 plus negative 6, does that equal negative 2? That is true. Let's use the second equation. 2 times my y, which is 4, minus 3 times my x, which is negative 2. Does that equal 14? Well, I have 8 plus 6, which equals 14, and that is also true. So this is my check step here to make sure the ordered pair I solve for does work with these two equations to make them true situations. Let's go on to example 2. Here we have 2x plus y equals negative 5, 2x minus 5y equals 13. Notice my variables are lined up, my x's are lined up, my y's are lined up, my numbers that stand alone are lined up. Now we're going to look at and see what can we eliminate anything here. Well, we can't necessarily eliminate because in order to eliminate for the 2's, for instance, one 2 would have to be positive, another one would have to be negative in order to eliminate that. For the y's, we would have to have the top equation have a positive y, the bottom would stay negative y to eliminate the y's. So we need to do something to one of these equations in order to eliminate. I'm going to take the first equation and I'm going to multiply each situation to the first by -1. So I do like a distributive property type situation here. So I take -1, multiply it by 2x to get -2x. Then -1 times y is going to give me a -1y or negative y. Then -1 times -5 is going to give me +5. I'm not going to multiply or distribute any value to the bottom equation because I already have just a positive 2x minus 5y equals 13. I can now eliminate because my x's will cancel out. -2 plus 2 becomes 0. That cancels. -1y minus 5y is going to give me -6y, which equals 5 plus 13 is going to give me 18. I now can solve for y by dividing -6 to each side. So y equals 18 divided by -6 gives me -3. So now that I've solved for one of the variables, I now need to substitute this -3 back into one of the original equations to now solve for my x. I'll just choose the top equation, 2x plus, whoops, let me scoot this over. 2x plus y equals -5. We said y we solve for is -3, so 2 times x plus -3 equals -5. I can add 3 to each side. So we have 2x equals -5 plus 3 is going to give me -2. To get x by itself, we divide both sides by 2 and get x equals -1. So we've solved for the variables x and y. X is -1, y is -3. We now need to check our work. In order to check, we plug in, we substitute our x and y values that we solve for back into each equation to make sure it's true. So the first one, we have 2 times x, so 2 times -1, plus my y, which is -3. Does that equal -5? Well, -2 plus -3 equals -5, so that is true. Looking at our second equation, 2 times my x, which is -1, minus 5 times my y is -3. Does that equal 13? Well, -2 plus 15 does equal 13, so that is also true. So my ordered pair that I solve for, -1, -3, is a true ordered pair solution for both of these equations. Last example here. Notice each example just gets a little bit more challenging, but it's all the same idea. We're solving the system by elimination. We first need to make sure the x's are all lined up, the y's are lined up, and the values standing alone are lined up. We then are going to see if we can cancel out either the x's or the y's. Here we cannot, so we need to think about what variable we are going to cancel. It looks like I'm going to cancel out the y's. We have 2 and 3, and if I multiply the top equation by -3, actually let's do it by +3, and we'll do the bottom equation, we'll multiply that by -2. You'll see why I'm going to multiply the top equation by 3 and the bottom equation by -2. For the top equation, we're multiplying by 3, so I distribute the 3 to each situation. 3 times negative 5x is negative 15x plus 6y equals 3 times 32 is going to give me 96. Then I have negative 2 times 2x gives me negative 4x. Then negative 2 times 3y gives me a negative 6y. Oh, look at my y's now can be eliminated, canceled out. Let's continue though, leaving left negative 2 times 10, which is negative 20. I now add the x's together, the y's together, and the numbers standing alone together. Positive 6 and a negative 6y, they cancel to become 0. Negative 15x plus negative 4x gives me negative 19x equals 96 minus 20 is going to give me 76. I solve for x by dividing negative 19 to each side. So x equals negative 4. Now that I solve for x, I need to plug in x into one of the original equations to now find my y. I'm going to just choose the second equation. Just there's a little bit more user-friendly numbers to work with here. So I have 2 times x. My x we said is negative 4 plus 3 times y equals 10. 2 times negative 4 gives me negative 8 plus 3y equals 10. Add 8 to each side. So I have 3y equals 18. To find y, we divide 3 to each side. So y equals 6. Now that I found my x and my y values, I can write an ordered pair. So my solution to the system of equations by elimination is negative 4, 6. We need to check our work to make sure this ordered pair does work and make these equations true. So if I look at my first equation, I have negative 5 times x, which is negative 4, plus 2 times my y, which is 6. Does that equal 32? Well, we have 20 plus 12, which equals 32, and that is true. Let's set this ordered pair up with the second equation. 2 times x, 2 times negative 4, plus 3 times y, 3 times 6. Does that equal 10? 2 times negative 4 is negative 8, plus 18. That does give me 10, and that is also true. So negative 4, 6 is the correct ordered pair for the system of equations.